Okay, let's jump right into this explainer where we're unpacking a really radical shift in how computers actually work. Think about it. Every web page you load right now is built from handwritten code. HTML gives it structure, CSS styles it, a layout engine handles the math, and then a renderer paints the pixels. But what if we just threw that entire pipeline in the trash? Today, we are looking at the transition to Software 3.0. This is a world where a single neural network essentially acts as your operating system, generating your screen pixel by pixel live as a continuous interactive video.
We have a ton of fascinating ground to cover. We'll outline the Software 3.0 vision, figure out how to solve speed and memory, fix autoregressive drift, translate inputs to actions, look at coherence and economic reality, and finally, map out the 4 neural tiers to get there.
All right, Section 1, the Software 3.0 vision, replacing the game engine. Let's start with the big picture and see how the foundation of computing interfaces is being completely reimagined.
In the world of Software 1.0, programmers literally sweat over every single behavior line by line. Honestly, even chatting with a modern LLM has been compared to typing into an old 80s DOS terminal, because the true graphical interface for AI just hasn't been built yet. But Software 3.0 changes the game. The neural network becomes so general that your prompt is the program, and the network itself acts as an intelligent canvas. Just one forward pass of a world model does the work of the game engine, the physics simulator, and the renderer all at the same time, giving you a playable environment straight from your input. Moving on to Section 2, solving speed and memory, the 60 FPS challenge. Because to make this interactive canvas actually feel responsive, developers have to overcome some massive mathematical and hardware hurdles. We expect our screens to react instantly, right? And that requires incredible speed. To hit 30 or 60 frames per second, a model only has a microscopic budget of 16 to 33 milliseconds per frame. That's a huge problem because standard diffusion models, the ones that generate images by taking pure static and removing noise step by step, normally take 50 sequential steps to finish. Doing that takes several seconds per frame, putting the whole process roughly 100 times over our tiny millisecond budget. So to close that massive speed gap, developers rely on a really clever process called distillation. Basically, they take a slow original model, which they call the teacher, and train a faster copy, the student. Through techniques like consistency models, this student is trained to agree with the teacher at every single noise level, which lets it complete the denoising process in just 1 to 4 passes. The absolute strongest of these pipelines can run up to 278 times faster. That is what finally makes real-time generation mathematically possible. But speed is only half the battle. The secret to keeping it fast is the key value, or KV cache. Once you're generating frames fast enough, you have to stream them autoregressively, meaning each new frame relies on every single prior frame. Without a cache, the whole system would just crash because the transformer would be forced to redo all of its complex attention math for every past frame over and over again. The KV cache solves this by acting as frame memory. It stores those past attention activations and reuses them. It's a brilliant factorization that keeps the computing cost per frame completely flat, no matter how long the user's history grows.
Next up is Section 3, fixing autoregressive drift, stopping the wobble. Even with speed and memory solved, generating sequential frames introduces a severe mathematical challenge that literally warps reality over time. Imagine trying to play your favorite video game, but the world just literally melts away after 10 seconds. Because the next frame is conditioned on the previous frame, which is the model's own output with tiny little errors already baked in, the next step inherits that error and adds even more on top. Frame by frame, this creates a compounding wobble until the original scene is completely gone. This autoregressive drift is exactly why today's bleeding-edge systems can only hold visual consistency for about 10 seconds to maybe 2 minutes before the scene totally falls apart.
To fight back against this drift, developers introduced 3 major training fixes. First, diffusion forcing allows the model to learn from a corrupted past paired with a clean present. Then, self-forcing trains the student model on its own actual rollouts, making sure the training data perfectly matches real-world inference. And finally, attention sinks. This is super cool. It pins the very first frames as permanent targets, meaning no matter how long the stream runs, the model can always reach back to stable, uncorrupted ground. Which brings us to Section 4, translating inputs to actions, the invisible control vocabulary. Once we actually have stable, fast pixels, the next puzzle is figuring out how human interactions steer this generated world without traditional code. Think about a normal video game. Your keyboard is directly wired to a function call in the code. Hit spacebar, the character jumps. But a neural world model just has one generic input slot. Early models like DeepMind's Genie 1 were trained on 30,000 hours of 2D gameplay video, but they had absolutely no recorded button presses in that data, zero. The AI had to literally invent its own way to understand actions, like jumping or running, just by observing how pixels changed from one frame to the next.
The solution to this is called a latent action model. The network trains a hidden vocabulary of discrete tokens, let's say 8 invisible buttons, and then it maps pixel changes to them. Basically, it invents a control vocabulary with absolutely no human button labels anywhere in the pipeline. At runtime, that slot becomes the network's input port. So whether you type the word jump, click your mouse, or even send an emoji, the system invisibly routes your input into this hidden vocabulary, translating your actions into direct screen control.
Now for Section 5, Coherence and Economic Reality, the Cost of Generation. The mechanics of generating and controlling pixels are coming together beautifully, but keeping the underlying system coherent and affordable is a really steep mountain to climb.
The big issue is that a pure pixel surface has the memory of a goldfish. It can't natively remember your open tabs, your draft email, or your scroll position. Keeping that hidden state coherent remains a primary challenge. To solve this, developers are kind of splitting their bets. One route is the neural OS, where a recurrent network holds the system's state in a hidden vector, almost like a traditional OS kernel, while the convolutional network paints the screen. The other route is a plain text scratchpad, where the model edits a literal text file right alongside the visual generation to keep track of state. Both are early, experimental attempts to force a stateless string of pixels to remember who you are and what you're doing.
And then there's the computing blocker. $15 million. That staggering number represents the rumored daily GPU burn rate for OpenAI's Sora before it was shut down. When you compare that to its reported $2.1 million in lifetime revenue, you immediately see the massive problem. The economic cost curve has to bend just as drastically as the capability curve before generating screens live every single frame becomes an actual viable technology for the average user. Finally, Section 6, the 4 neural tiers. The staircase to the future. To contextualize all of these breakthroughs and bottlenecks, researchers don't view the path forward as a single leap, but rather as a practical staircase spanning the next decade. We're currently scaling these 4 neural tiers. Tier 1 is exactly where we are today. AI might write the HTML, but your conventional browser still renders it. Tier 2 introduces generative regions, where specific parts of your screen are purely generated pixels with no HTML underneath. Tier 3 brings full generative loops, but restricted to narrow domains like specific video games. And finally, Tier 4 is that grand, long-term goal, a world where a neural substrate handles all the complex visual rendering, but it's tightly integrated with deterministic tools, traditional, reliable code. Because while neural networks are amazing for generating what looks right, you absolutely want traditional, bulletproof code handling your bank transfers and verifying your identity.
As we wrap up this explainer, we are left staring at the ultimate challenge, and that is reliability. A neural model's physics are always approximate. Going from a 90% impressive demo to 99% reliability is incredibly hard, and pushing that to 99.9% is exponentially harder. Every new 9 in that sequence costs as much as the last. So we really have to ask ourselves, can this march of 9s eventually allow approximate neural simulation to conquer those final fractions of a percent? Or will our future operating systems forever need to be a careful hybrid, balancing the boundless creativity of a neural canvas with the rigid, flawless math of the traditional world? It's a massive question, and it's the one that will absolutely define the next decade of computing.